Second thing we want to talk about, building big matrices. We're going to build that big A matrix today. And I'm going to teach you how to use, okay, so today, you know, a lot of people use FFTs. And there's nothing special about that. That just means you're a player in the game. We're going to learn SP diags today. That takes you up a level. Because not a lot of people know that. They don't even know what you're talking about. And you're like dropping on them like, oh, yeah, you don't even know that? Yeah. That's what I walk around doing all day on the Ave. I'm one of those crazy guys. And it turns out those dudes don't know SP diags. All right. So here's what we're going to do. We're going to make this matrix. And we're going to make it to be we're going to chop it up to 5 points in each direction. In the x direction, 5 points. Y direction, 5 points. So our matrix, remember, is not a 5 by 5. Remember, we're going to restack our data. It's going to be 5 times 5, so 5 squared, right? So this is going to be our discretization in x and y. And that's going to be then the size of the matrix we're going to work with. Okay. So first of all, let's talk about this matrix A. And let's talk about what we want to put in here. So first of all, I'm going to make a vector of 1s. Big vector of 1s. And what I'm going to do is I'm going to make this what's called the SP diags command. And what this is, SP diags means sparse diagonal. Diagonals. There's an S in there. It's a sparse diagonal matrix. It means what you're going to do is you're going to basically say it's going to be a matrix with full of zeros, and you're going to tell me which diagonals have stuff in them and put stuff on those diagonals. So for instance, here's how you might put something in. So first you tell it, let me give you the structure here. It's going to be an n by n matrix. It doesn't have to be. You can tell it what size it is, but for us it's an n by n. You tell it the location of where you want to put this thing. So for instance, if I want to put something on the diagonal, it's 0. If I go to the right of the diagonal, it's 1, 2, 3. Go to the left, it's -1, -2, -3. So your location is predicated off that diagonal, to the right or to the left. So if you say 0, and what I'm going to do is lay down an E1 on that. So right now what I've made is essentially the identity matrix. Here's another command. Spy. Spy allows you to look at all the non-zero components of the matrix. So if I do this, press go, there's my matrix structure. The blue dots indicate which things are not 0. By the way, by using the SP diags, the only things it saves is the blue dots. Notice the matrix is sparse. It's almost empty. If you were to save all these zeros, right, it's order n squared matrix, the memory requirement would be order n squared for you to save all these things as zeros. If you save it as a sparse matrix, it's order n. Okay? Be easy on your chip. Try not to save memory stuff. You're going to have to use your memory for other things besides saving matrices. Okay? So this is what's nice about this. So hey, look at that. I put down a diagonal. And by the way, if you come over here to your MATLAB code and say, what's A? Notice how A is saved. The 1/1 component is 1, 2 is 1. It only saves what it needs to. Okay? So normally when you say A, it prints out this giant matrix to your screen. And it's just saying, look, here are the components that are non-zero. Yeah?
You wanted to add like 0.68 equals 12. Do you blow the sparseness? Or can you say A bracket 6 comma 8 equals 12? Do you then add that point?
Yeah. So you can do this.
Sparse?
Check this out. Yeah. A 6 comma 12 is equal to 7. Because we like 7, right, Taylor? Huh? It's the best number ever. And then we could just say spy that and check it out. There's Taylor's number right over there. It's a 7. It's still sparse. You can do anything you want now. Okay, we're going to keep that there. And then, by the way, I can put down diagonals anywhere I want. Let's put down another row of 1s at 1. Look at that. I'll put it one diagonal over, because I said go to 1, which is the next one over, put down 1s. Now, our matrix is a little more complicated. I encourage you to look at page whatever in the notes, where I actually show you what this thing looks like. Okay? And this thing has a complicated structure. In particular, I guess we could... Actually, I have it in my notes. So let me draw this, what this thing looks like. Do we have kind of lights up here real quick? And then, all right, so let me just show you what this thing looks like. Okay, what page am I on? Okay. Okay. Sorry. There. Okay, ready? Okay. A is the following. -4 on the diagonal. Ready? This is what makes it complicated. 1s. And then an occasional 0. And then 1s. And then an occasional 0. Pain. We'll get it, though. By the way, it's same over here. 1s, occasional 0s. The 0 is 1 down from here. So this 0 is in that first n by n block. Sorry. No, it's not. It's 1 over. Sorry, that 0. There's an n by n block there, then it's 0, and then 1s. Okay? So forth. And then this one here, the 0 is 1 down here, and then 1s. Okay, so I got 3 rows. 6 more to go. All right. Then we have these. This is all due to periodic boundary conditions, by the way. That's why these appear. Then you have these 1s on the corners. And then these 1s over on these corners. Got 5 diagonals. Then I have some 1s over here that continue over there. Then I have some 1s over here, continue there, that continue there. So how many I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. That's what it looks like. So obvious. No. Okay. That's what we know. Now, notice what a pain this is. Just so I can give you more headaches. By the way, you only have to build it once. And we're going to have the code right here, right now. So it's not even you have to build it. It's just we'll have the code right here, right now. I have to put 1s with an occasional 0 down. And then I got to put 0s with an occasional 1s down. And then I got to put some 1s on the corners. Okay, so kind of problematic because these guys and these guys are painful. I've got to figure out how to do that vector. Okay, so we'll do that. But for right now, let's do some easy things. Let's put down these 1s, these 1s, these 1s, and these 1s. Notice where they go. This starts at n plus 1 in. Right? This is a little n by n block. Or in my notes, I think that means it's an m by m block. It's n by n. These are m by n's, m by m's. Okay? You know what? If you say, you said m, I said, no, you didn't hear me right. And you wouldn't know for sure if I said n or m. They're so close. I could lie. Okay. So put some 1s down here. This is the last m by n block. Put some 1s there. This is n plus 1 down. Put it there, put it there. So let's put these 1s down because that's easy. And then we'll work on those last 4. Everybody go with that? Okay. We'll start this back up. We can have the lights back down. Mood lighting. Here we go. So first of all, I guess we'll have to do that. Get rid of that 7. So first, let's go ahead and put in those 1s. So first of all, we have -4 on the diagonal, not 1. Second of all, we have 1s on the edges. We have 2 1s out there, and then we have 2 1s over here. And where are they located? Well, the 2, if you look at what we did here, and in my notation, this is all the way at -n minus m. And this is at minus m. And it's 5. So there are 4 by 4s that are sitting inside of these things, right? Because I've picked 5 points, but really it's the interior 4 that matter. Okay? All right. And then over here, I have m and n minus m. If I do a SPY on that, here's what I got so far. Look at that. Kind of nice. Laying down some diagonals. Everybody cool with that? All right. I've laid down the easy ones. So what I'm working with is the M I picked is how many points I'm going to have in this way and this way. So right, I have 5 points, but remember the last point's the same as the first, so it's really 4. And 4. That's why I come down here and say I have a 4x4 block right here, and at the 5th location, I drop this. I come all the way down to N, which is the last one, come back up, drop it down. Same thing I do there. So now we have to drop some matrices in here, or vectors in here with ones with occasional zeros and zeros with occasional ones. Okay, so how do we do that? So let's come to here and let's build a 0 vector. E0 is zeros n by 1. This is a vector of zeros. Okay, and what we're going to do the following. First of all, let's make a vector called E2, which is just E1. So I'm going to copy the 1 vectors. And what I'm going to do with E2 is I'm going to occasionally put in a 0. How often do I put in a 0? Well, every mth point. Remember, m is the small matrices in there. And by the way, part of your homework 3 is going to be all about convincing yourself about this stuff. Because you're going to immerse yourself in building matrices. That's all homework 3 is you've got to build a derivative matrix, an x, and y, and then this. So what we're going to do is for j equals 1 to m, because that's how many m blocks I have. Remember, n by n, and I have these m by m blocks, and there's m of them. And I'm going to go down for each block, and what I'm going to do is the following. For E2, put an occasional 0. Right? So J is going to, one second, J is going to go 1. So the first thing it's going to do is, first thing it's going to go, say, well, m is 5, so it's going to go down to the 5th component, put a 0. And then J is going to be 2, it's going to go to the 10th component, put a 0. Right? So it's a bunch of 1s, 5th component, 10th component, 15th component, all the way down. Put a 0. Okay? Yeah?
So if you have a longer vector than your diagonal is long, does it just take the first portion, kills the excess?
Yeah, remember, so these things overrun over here, and they run over here. And it just goes this way. Everything's lined up according to here.
Wait, so that bottom, the negative diagonal, the diagonal negative, whatever it was, it got rid of the first section of the vector?
Yeah, right here. So it thinks about putting the vector down right here. It says, well, okay, you put the vector at the start of here, go down. So I'm obviously not going to show that because it doesn't exist.
Okay, and at the other side, it gets rid of the end of the vector?
Yes.
Okay.
Or it could be, actually, I think that's wrong. It's the other way. It goes this way. So these guys here get stuff thrown out down here. And this stuff up here gets thrown stuff up there. Okay? But same concept. So let's put this E2 in, because we just basically created the z vector with an occasional 0. And that guy goes right here. If I do this, oh, come on, come on. Look at that. Oh, sorry. I got to tell it where to do this on the -1. Sorry. There we go. So I put down this E2. Look at that. See that? So what SPY is powerful for us? Say boom, 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 0. Boom, 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 0. Boom, boom, 0. Got it. Now the other one is interesting because it's up here and it's up this. It's this one here. That's where the 0 sits. So it's like E2, but just shifted up by 1. Okay? So I could take this E2 vector and just shift it all. Okay? Which I'm going to do. All right? And then but first let's build the zeros with the occasional 1. So let's make a vector called E4, which will be just a bunch of zeros. And now what I'm going to do on this one is put an occasional 1. So E4 just like this guy, equals 1. So now there's the occasional 1, there's the occasional 0, and I put this E4, actually this one here, interestingly enough, and we won't have time to talk about everything yet, but I'll show you where it goes. It actually goes over there. Occasional 1. Now the thing is, when I put this one over here, I have to shift it by 1. This one here gets shifted down. This one here gets shifted up. Ready to shift some stuff? Remember, we only have to do this once, right? So it's an upfront cost. Okay? It's your investment. And then once you have it, you can have this forever. Anybody ever asks you, hey, I need to take a Laplacian with periodic boundary conditions, you'd be like, dang, I got you. You just take this matrix, which you built in 2011, and you can apply it any time in your life. Okay? Show your grandkids, whatever. All right, yes?
Where that needs to go in the...
This one here?
Yeah.
Dang, I didn't, did I?
Where does it put it if you don't put it in?
That's a good question. Let's just put it in, don't ask hard questions. All right. That one's supposed to be there. No. M minus 1. That's where it's supposed to go. I think it put it, well, who knows? That's sorry. There we go. Good catch. All right. So now let's shift some stuff. Shift happens, and you guys just deal with it. So here we go. Shift to everybody. Let's shift. We're going to shift E2. Ready? We're going to make a vector E3. I don't know if I have time to do it. Here's how it's going to work. And let's just see if you are chill with this. I grab the first 1 through n minus 1 components of E2, and I make it the second to n n components. Sorry, that should be a comma. So I take the first 1 through n minus 1 of E2 and make it the second to n components here. And then to finish this off, I take the last component of E2 and make it the first component of E3. And I'm going to drop E3 right here, and this is at 1. Go. There it is. See that? I just took this, shifted it up, dropped it down. All right. Let's finish this off. Let me take this row here, this E4, and I'm going to shift it down 1 over for here. And I do this the following way. I say, I'm going to make a vector E5. And the way this works, same thing. 2n1 is equal to E4. And the first component is the last component. And I put this E5 right, right over here. E5, and this is at minus m plus 1. And if I spy that, there it is. This is the matrix we built in class. Part of your job is to convince yourself you feel comfortable with it. And the blue dots are the only things you save. Now, let's take a look at this when we scale it. Because nobody's going to solve this thing on a 4x4 domain, right? I mean, you're going to need a lot more points. You might say, I'm going to chop up my X domain into 100 points. And then you spy that thing, and boom, this thing's huge. It's 10,000 by 10,000 matrix. Okay, so this is kind of what we're looking at. We're going to be working with that matrix. Now, you see how white that is? That's because there's all zeros there. You don't want to save all that. Do you know how many components you have to save? 10,000 by 10,000? I'll let you do the math in your head. Right? This is huge. 10 to the 5 squared, if you want to save this in memory, you got to eat up all that memory to save a bunch of zeros. SB diags changes your game. Brings you up a level because now you can do this thing with sparse things. Now, one last thing I want to do. Let's go back down to 5. And we're not only 5, we're going to say, hey, what's the determinant of that matrix? That's not 0. Let's do the condition number. (10 to the 17). If you see a number like this, that's bad. Okay, so the condition number is the measure you want to look for. Because that determinant actually said, oh, 10 to minus 3, that's not, I mean, that's pretty far away from 0. All things considered. The problem really comes if you look at the condition number. And if you have a condition number, anything above here, like when you start getting 10 to the 5, 10 to the 6, you're kind of like, ooh, that's kind of looking singular. 10 to the 17 says, dude, I am totally singular to you. That's the interpretation of that. Okay? If I wrote MATLAB, I would have a little thing. If it says, I'd say, dude, that is totally singular. So just so you know, don't be messing around with doing backslash with that matrix. Okay? All right, that's it for today.